Okay, so we're in Introduction to Statistical Learning, Chapter 6, Question 10. So it's multi-part, so we'll come to them as we come to them. But the thing that we're exploring here is just the basic phenomenon wherein as we add explanatory parameters, our training error will go down, but test error may or may not. So let's start here. So in part A, we're going to generate 1,000 observations with 20 features, in other words, 20 parameters. Okay. And some of these parameters, these betas, some of this 20 will be set to be 0. Okay. So here I'm just generating some betas. Okay. So first I'm going to generate 15 that are not 0, okay, and then I'm going to set the other ones to 0, and then I'm just generating some data here for x, and you can you can look at that for yourself. I mean, these are, there's nothing special about what I've done here. I've just kind of thrown some stuff together. And now we're going to combine the x and the beta as well as an error term, epsilon, and a intercept. Now, this model does not ask for an intercept, but often the intercept is assumed to be in the x, in the capital X here, in the X matrix, but it's not here. And also this will make later, some of the later operations easier. So I'm going to wrap all of that up into y. So y is a plus all of the x's times their respective betas plus the epsilon. Now, if you're not familiar with this operator right here, this is matrix multiplication in R. So that takes every x, set of x's, times its corresponding beta value. So anyway, it's not really important here. The important thing is that we have a y here that is some function of x and beta and so on. Okay. So now we're supposed to split our data, which we just generated, into a training set and a test set. All right. So I have my data frame here, and so I'm just calling it y and x. Okay. Or I'm calling it d, and it's comprised of y and x. Okay. And so I want 100 training observations. So I set train in to 100, and now I'm going to randomly sample 1 to 100, or 1 to 1,000. I'm going to get 100 samples between 1 and 1,000 where I'm not replacing any of the values. And now I just set my training data to subset D by the training index, which we just generated, and then the test data is everything else, so minus training index. Okay. All right, so now for C, we're going to perform best subset selection on the training set of data, plotting the mean squared error associated with the best model of each size. Okay, so for this we need to install and load the LEAPS package. Okay, I've already done this. And then we use the reg subsets function that's in the LEAPS package, and we're regressing y on everything in x using the training data, and we have up to 20 predictor variables, so we go NV max here. Okay. So then we're just going to simply plot. So I summarize that data, and then I am just simply plotting the best model for each number of parameters here. Okay, and so this is what we get. Okay, as we should expect, the best performing model on the training data is maximum parameters. So when you do this, you might want to be, or I would guess that you'd be, 18, 19, 20 would probably occur most of the time. So. Okay, so now parts D, E, and F, they're all very related, so I just kind of put them here into one thing. So we're gonna use the test data and plot the test mean squared error. So the best the mean squared error for the test data for the best model of each size. That's a mouthful, and I apologize. So, but basically making this plot, but based on the test data. Okay. Well, let's just look at what that plot looks like here. Okay, so this is what that plot looks like. Okay. So again, this is on the test data. So we shouldn't expect necessarily the same outcome as what we got with the test data. And here we see that it's 15 parameters happens to do the best. And this is interesting because if you remember our data, we have exactly 15, so Pn is 20 minus 5, 15 non-zero beta parameters, okay? And so our test model happened to pick up on that, okay? So the part E here is for which model size does the test MSE take on its minimum value. So we've already found that in the plot here. It's 15. Okay. And then how does this model compare to the how does the model at which the test MSE test set MSE is minimized compared to the true model used to generate the data? So we already discussed that. It just so happens that the best model here happens to align with how the data was actually generated. So what I've done here is I've taken the estimated betas from the P equals 15 model, and then compared them with the assigned betas. Okay, and you see that they're reasonably close in basically all instances. Okay, but I think what's more important here is that this model correctly picked out the model by which the data was generated, or at least in terms of the number of parameters that went into it. So that's interesting. Okay. And now here for part G, the last part, we're going to create a plot that is displaying this statistic, and I'll talk about that in a second, for a range of R values. Okay, so R here is just being defined as the coefficient estimate for the best model containing R coefficients, so between 1 and 20, right? That's how many coefficients we have, I guess, plus the intercept, but I'm going to ignore the intercept here. Okay, comment on what you observe. Okay, so what I'm going to do here is I'm taking a sequence of R values, 1 to 20, that's the number of parameters, okay? And then I'm going to create this vector that I'm going to fill up. So I've created this vector called S, and it's just going to be of length rseq, okay, 20. And then for 1 through 20, for R in length 1 through rseq, 1 through 20, I'm going to do the following. Okay, so first I'm going to call up reg summary. Okay, I'm going to call up this guy that we made way up here in part C. Okay. And again, what that's, in fact, let me just show you what this does here. Let me do it way down here, to show you what this looks like. Okay, so if I call reg summary and then grab the which object, okay, we get each model that was tried, 1 through 20, so 1 being, the model where only, the best model where only 1 predictor variable was used. 2 is the best model where 2 predictor variables are used, okay? So in 1 here, it's x11. In 2, it is, the 2 of them are x3 and x11, okay? Now they all have the intercept being true, so we're ignoring the intercept here, okay? So going back up here, so what are we doing? So we're taking the model we're taking the best model for R coefficients, and then this little subtract 1 here, that just means that in each of these cases I'm ignoring the intercept, right? So that's how I grab this true, false, true, false, true, false vector here without the intercept, okay? Again, that's just to make all of these things match up, because when I assigned betas, I didn't assign an intercept, okay? And we're not asked about the intercept up here necessarily. Okay, so anyway, so we have that. And now, so I want to grab the assigned beta values that I generated randomly at the very beginning of this. I want to identify, I want to grab the ones that are true in the best model of size R. And then I want to grab the corresponding betas that were estimated from the best model of size R. Okay, and so I do that with this guy. Okay, again, ignoring the intercept. Okay. And now finally, I'm going to build this test statistic here. So it's the square root of the sum of the squared difference between assigned and estimated betas. Okay. And so now when I plot that, I get this guy right here. Okay, where the best performing model in this case happens to be beta or p equals 1, or you know, just where r equals 1. Okay, now that seems a little bit suspicious to me, and so I'm actually not entirely sure that I understood this question correctly, because that seems a little bit anomalous. But one thing that I did recognize is if I come way back up here to the top, so I set the seed at 1, and I'm going to leave it there in the collab sheet. But if you set this to another value, then this guy, the best value here, will obviously jump around. And about half of the time, I guess, roughly speaking, is what I found, it lines up with the best model on the test error. Okay, so I guess that's a little bit above chance, and so I guess that there's some correspondence between this statistic and the test MSE, but it's not very strong and seems to be heavily contingent on, you know, the random seed that you set at the beginning. So make of that what you will. I guess if you have an intuition as to why that may or may not be, then maybe leave it in the comments. I'd like to learn if anybody has some insight into that. Okay, we'll call that good.